All right. Well, if we look at example one, so we've got our manager wants to know which days of the week her employees are absent in a 5-day work week. Most employers would like to believe that their employees are absent equally during the week. She tracked the next 60 absences and recorded on which day they occurred, and the results are shown in the table below. Do the absences occur with equal frequencies during the work week? Use a significance level of 0.05. So if we add these up, since there's supposed to be 60 absences, we should get 60 for our number of absences. And so again, these were tracked by the individual, so these are our observed data. And so what we're trying to do is figure out what our expected data is. So their claim is that absences occur with equal frequencies. So that just means in a 5-day work week, if there were 60 absences, if we take 60 divided by 5, then that should give us, oh, not 15, 12, sorry. Give us 12. So that means that on Monday there were 12 absences, Tuesday there were 12, Wednesday 12, Thursday 12, Thursday, Friday 12. So again, this will equal 60, which is what we want. So that's going to be our observed and our expected for this one. So this looks perfect. So again, our hypotheses for these are going to be the same for all of them. So O is not equal to E, H naught is O equals E. And again, we're at the alpha equals 0.05 level for this one. So now let's go ahead and take a look at how to calculate our test statistic. So we don't actually need this. You can kind of ignore all this stuff. This is if you were trying to do everything by hand. So I'm going to show you a cheat that allows us to do it in the calculator much, much easier in this case. So I will jot down what our test statistic is. So chi-squared of t is the sum of all of our O minus E squared, all divided by E's. So what we're going to do is use our calculator and our list as a way to actually calculate this in a much, much more efficient way than trying to do this by hand. So what we're going to do is we're going to put in list 1 our observed data, and in list 2 our expected data. So let's go ahead and do that first. So let's go ahead, switch over to the calculator real quick. Go to Stat, go to Edit. I'm going to go ahead and clear out my list 1. And so I want to go ahead and type in the observed here. So I've got 15, 12, 9, 9, and 5. Whoops, 15, sorry. And then for our expected, everything was just 12s for all of them. All right, so perfect. So now we're going to use some commands we haven't used before here, so I'll show you where they are exactly, but let me write them on the other sheet real quick first. So the way this is going to look in the calculator is we're going to do the sum command of L1 minus L2 squared, all divided by L2. And so technically I should have another parenthesis here. So that's actually what we're going to type in our calculator when it comes time to do this. And we do this, it does all that calculation in the background. So even though there's multiple things in the list, it'll do the subtraction, it'll do the squaring, it'll do the dividing, all that kind of stuff happens magically in the background. And again, there's a lot less room for error on our part or even just rounding mistakes, which can happen doing this kind of technique. All right, so now that we know what we want it to look like, let's go back to the calculator and make that happen. So if I go to, or quit out of this real quick, so hit second mode to go back to the main screen. So what I'm going to do is I'm going to go to second stat to get into list mode. And if we go to math, one of the options under that list is sum. So let's go ahead and hit our sum. And so notice this comes with a parenthesis already. So that was kind of that extra parenthesis that I added. So all I need to do now is do my next parenthesis, my list 1, so second one minus second 2 to get list 2, and then all squared, and then divided by list 2. So that's what it should look like in our calculator, and when we hit enter, it should give us our chi-squared test statistic for this guy. So let's hit enter, and so it looks like we ended up with a chi-squared t-value of 3 in this case. So let's go ahead, flip back to the screen here. So our chi-squared sub t looks like it's just plain old 3 for this one. So now let's go ahead and find our chi-squared comparison for this one. So what we've got is we know that we have 5 categories. So we have 5 categories, Monday through Friday. And so that means our degrees of freedom is going to be 4 for this guy. And so our alpha is 0.05. So if we go to our chart, we can figure out exactly what our chi-squared sub c would look like for this one. So I'm going to scroll back to where our chart was in the last section. So again, we're using our 0.05, but in this case, we're using a degrees of freedom of 4. So we end up with 9.488 as our chi-squared sub c, our comparison statistic. And again, that's from the chart. And so again, our alpha of 0.05 is going to be way over here on the left. It's probably actually going to be further over technically, but just to give it somewhere. So our 9.488 is going to be our chi-squared sub c. And if we look at our 3, our chi-squared sub t is going to be way over here. And so again, just like before, if we're in the shaded, we reject H naught. If we're in the white, we fail to reject H naught. So according to this, it looks like we're going to fail to reject H naught. It doesn't look like there's significant evidence to prove that there's a difference between the observed and expected. So let's check our p-value just to make sure that's actually the case. So for this, we're going to get p equals chi-squared CDF. And so again, our lower bound of 3, some ridiculously big upper bound. And then again, our degrees of freedom of 4. So if we throw this in the calculator, so our chi-squared CDF is in the same place where TCDF and normal CDF was. So we're going to hit second vars. And so notice chi-squared CDF is number 8 on our list. So 3 comma some ridiculously big number comma 4 gives us 0.5578. So what that's saying is 0.5578, that there's a 55.78% probability that that expected distribution could happen at random. So again, there's nothing out of the ordinary, nothing ridiculously unexpected about that expected column. That could happen most days. So it's definitely greater than our 0.05. So again, we're going to fail to reject H naught. So again, our conclusion is that there isn't sufficient evidence to prove that these two distributions are different, that the expected and observed are that much different. So there isn't sufficient evidence. These two distributions are different. All right. Well, hopefully that makes sense to everybody. Again, look through it on your own. Make sure it all looks good. I've got some practice problems that I'm going to be, again, dividing up between the different groups. So look to see which group you're going to be working with in the collaboration space. And when you're done with those, we'll come back and we'll hit the next type of chi-squared hypothesis testing that we'll be doing, which is going to be test for independence. So good luck, everyone.